Let's talk about thin film interference. What does this mean? Well, it's kind of redundant. Film already means something really thin, a thin amount of substance, and thin film means really, really thin. So how does this happen? It can happen naturally. When it rains outside, there'll be puddles of water, and because there's oil left over on the road, sometimes some oil will float on top of the water, and it's often a very thin, small amount of oil. In other words, the thickness of the oil floating on the water is extremely thin. So we'll call this thickness T. How do we know it's thin, and how do we know it's there if we can't see it? We know it's there because if you look down at it, if you look down at the water, you'll sometimes see a colorful pattern in here, and that colorful pattern on the top of the water, streaks of red and blue and orange and green, happen because of thin film interference. It also happens in bubbles. If you blow a bubble and then you hold it on the bubble wand, you'll see that there's these colors in there. And those are coming from thin film interference. How does it happen? Well, light comes in. So this might be from the sun or whatever, some source of light. Comes in here. That's only one light ray. We need multiple light rays to get interference. So what happens when it hits the oil? Part of it is going to reflect off the top of the oil. So it's going to reflect right back on top of itself, but if I were to draw it right back on top of itself, this would get messy really fast. So I'm going to draw it over here, but know that this light really reflects right back on top of itself if it was coming straight in. We'll call that light ray 1. But that's not all the light does. Part of it reflects, but part of it continues through the oil. So in order to get thin film interference, there has to be the thin film has to be translucent. It has to let light through. Not just reflect it, but let light through. So some of this light ray is going to continue on through, like that. But what does it do? It meets another interface. And every time light meets an interface between two medium, well, it's going to reflect and some of it's going to pass through, refract. So in this case, some of it reflects off of this interface. So we had a reflection here, and we had a reflection up here. Both of these were reflections. And so some of this light comes back up. Again, I'm not going to try to draw it right back on top of itself. I'll draw it over here so that we can see them. So it comes up. Now these overlap. Look at, now that these are overlapping, wave 1 and wave 2, now my eye can experience interference because these two waves are going to hit my eye. They might be constructive, they might be destructive, and I might see different colors in here depending on the wavelengths. That's what we want to try to figure out. How does the thickness of this oil and the wavelength of the light determine whether this is going to be constructive, destructive, or neither? Here's what we're going to do. We know we're not going to stray from what we know. What we know is that to get constructive interference, when we have two light rays, what matters is the path length difference. So if the path length difference is 0 lambda, right, any integer lambda, you can just call this m lambda if you want, that's going to be constructive. And anytime the path length difference is going to be half integer lambdas, so half lambda, 3/2 lambda, and so on. If you wanted to, you can call this m plus a half lambda. These are going to be destructive. I guess that doesn't equal constructive. It implies constructive and destructive. But remember, there's a got to be careful. It can be weird here. These are flip-flopped if there's a pi shift between them. If one of these gets pi shifted and the other does not. If one of the waves is pi shifted and the other is not, remember, if this was the thing with the back of the speakers, if you flip the wires on the back of the speakers, now instead of the speaker wave coming out like that, speaker wave comes out like this. Now, if you overlap these, this condition gets flip-flopped. If you forgot why, go back and watch that video on wave interference. So this is the condition. Integer wavelengths give us constructive, half integer wavelengths give us destructive, unless one is pi shifted. If they're both pi shifted, then this condition still holds. But if only one is pi shifted, you flip-flop these relations, and the half integer wavelengths give you constructive, and the whole integer wavelengths give you destructive. So, does that happen here? Do we have to worry about pi shifts? We didn't with we didn't with double slit. Remember with double slit, shoot, we didn't worry about any pi shifts, but that was because one wave came in, and now these were both from the exact same wave, so we know they started off in phase. How about these waves for thin film? Could there be any shift in pi? Well, there can. Every time there's a reflection, there can be a pi shift. I repeat, every time light reflects, there may be a pi shift. How do you know? It depends on the speed of the wave in those materials. So let's say we had air out here. So light has some speed in the air. Turns out the speed in air is about the same as the speed in vacuum, 3 times 10 to the 8th meters per second, but I'm just going to write it as V air out here. And then you have a certain speed of the light. Light will travel a certain speed in the oil. So V oil in here, this is going to be less. Let's just say, for the sake of argument, V oil, the speed of the light wave in the oil is less. It's got to be less. Let's just say it's 2.7 times 10 to the 8th meters per second. And in water, again, it's going to have a speed of light in the water. Let's say the speed of light in the water, well, we don't have to say. We know that's about 2.25 times 10 to the 8th meters per second. So how do we determine, knowing these speeds, whether there's going to be a pi shift or not? Here's how we tell. Every time light reflects off of a slow substance, there's a pi shift. So what do I mean by that? Well, the light here started off in this material, and did it reflect off of a slow substance? It was in air. That's pretty fast, 3 times 10 to the 8th. It reflected off of oil. It reflected off of a medium where it would have traveled slower. So this reflection right here does get a pi shift. There is a pi shift for this reflection. The light wave that came in, if it came in at a peak, then it's getting sent back out as a valley. And if it came in as this point going up, it'll leave as this point going down. It's going to get shifted by 180 degrees or pi. How about this one down here? Did it reflect off of a slow medium? It did. It was in oil. It would have traveled into water, which is slower than the oil, and so this one also gets a pi shift. And same thing, if it came in as a peak, it will leave as a valley. What does that mean for this condition up here? Well, if both are pi shifted, it's as if neither of them get shifted. If we flip both of them upside down, well, everything's cool again. We've just made everything back to where it was. So we would not swap these conditions in this case. If, for some reason, we use something besides water, we use some other liquid here, and this liquid had a speed of, instead of 2.25, let's say the speed here was 2.85 times 10 to the 8th. Now, well, that doesn't change anything up here. This is still getting a pi shift. It was in air. It reflected off of something slower, oil. And by slower, I mean if the light traveled into it, it would travel slower. So that gets a pi shift. But now this one down here, this light ray that was in the oil, would have gone through water. It reflected off of, oh sorry, this isn't water anymore, this is some new liquid. It reflected off of this liquid that it would have traveled faster through. So does it get a pi shift? Nope, there'd be no more pi shift down here. Only one of these reflected light rays get a pi shift, and if that ever happens, if one of the light rays gets pi shifted and the other does not, then we would swap these conditions, and it'd be the half integer wavelengths that would give us constructive and the whole integer wavelengths that would give us destructive. So let me just be clear here. Let me show you what I'm talking about. Let me clear this off. If I had a material, and right here it's slow compared to this one, if it reflects off of a fast material, no pi shift. No 180 degree shift. But if it's in a fast material and it reflects off of a slow material, then yes, this gets a pi shift. So this gets a 180 degree shift. That's how you determine it, is whether it reflects off of a fast material or if it reflects off of a slow material. For both sides, the top two up here, got to ask the same question. Did it go from slow to fast, reflect off of a fast, or did it reflect off of a slow? That's how you determine. If it reflects off of a fast, no pi shift. If it reflects off of a slow material, then it does get a pi shift. Okay, so that's how you deal with pi shifts. Let's go back to this one. There's a few more details here. People have a lot of trouble with thin film, to be honest. That's one problem, is they don't like figuring out whether it was pi shifted or not. It's actually not that hard once you know the rule. But there's another problem here. What's delta x? We never even said what delta x is. Well, it's got to be related to the thickness. So imagine this. Both waves come in. Imagine both waves are combined in this big wave coming in. They were both in there to start off with. So they both traveled that distance. Wave 1 reflects off and just travels this distance. Wave 2 also travels that distance, but only after wave 2 traveled this extra distance within the thin film. So the extra path length that wave 2 traveled compared to wave 1 was not the thickness t. Here's where people make the mistake. People think that delta x for a thin film is t. No, the wave 2 had to travel down and then back up. So it's 2t. So this is the key. For thin film interference, the path length difference will always be 2t. So I just have to come up here. I know what delta x is. For thin film, it's always going to just be equal to 2 times the thickness of what? The thickness of the thin film. So I'm going to put 2t here. This is my condition. This is how I change this to make it relevant for thin film. For double slit, delta x was d sine theta. For the thin film, delta x, the path length difference, is just 2 times t, so it's kind of simpler. You got these pi shifts to worry about, but the delta x is simpler. Alright, so that's not too bad. Anything left to worry about? Yes, one more thing to worry about.